Hi everyone and welcome back to another lab. In this session, we will walk you through the process of configuring and verifying Layer 2 Link Aggregation Control Protocol. We will start with a brief overview of what LACP is and how it works. Next, we will discuss why we would need to use L2 LACP protocol. And then after that, we will outline the lab objectives, review the lab topology and the lab tables, and walk you through the lab tasks. Finally, we will guide you through the solution step by step. By the end of this session, you will have a thorough understanding of L2 LACP and how to use it effectively in your network. Not to mention that this lab will also help those that are looking to obtain their CCNA qualification. Okay, so what is LACP? Layer 2 Link Aggregation Control Protocol is a network protocol that provides a standardized method for combining multiple physical network links into a single logical link, known as an Ether channel or a link aggregation group or LAG. The LACP is part of the IEEE standard, ensuring compatibility between different vendors' devices, and it can dynamically detect and aggregate links between switches or between a switch and a server, enabling automatic configuration and management of lags. The LECP monitors the health of links in the lag and can automatically remove a failed link from the group and add it back when it recovers. And by doing this, it increases continuous network operation. The LACP traffic is distributed across the member links in the lag based on various algorithms to optimize the bandwidth usage. Okay, with that being said, let's discuss how LACP works. So, devices using LACP periodically exchange LACP data units or LACP DUs to communicate and negotiate the aggregation of links. And LACP can operate in two modes: the active mode, where the device actively sends LACP-DUs to initiate the formation of a lag, and the passive mode, where the device responds to LACP-DUs received from the active mode device but does not initiate the formation of a lag on its own. So, as you can see from the table I included in the lab and the document, in order for layer 2 ether channel to work, at least one of the switches must be set in active mode. If, however, both switches were configured in passive mode, the ether channel will not form. So, now let's quickly discuss the benefits of using LACP. So, by aggregating multiple physical links, LECP provides higher aggregate bandwidth. For instance, if you bundle four 1 gig links, the total available bandwidth becomes 4 gig. The speed of a single data flow, however, a single file transfer, for example, is still limited by the speed of a single data flow. For example, a single file transfer is still limited by the speed of one of the individual links. For example, even in a 4 gig Ether channel, a single transfer would still travel at the speed of a one link. In this example, we would say 1 gigabits per second in this case. Think of this as when you are traveling on the highway, you can drive on a highway road that has a single lane at the speed of 70 miles per hour. If, however, there are lots of other people traveling at the same time, you might experience some delay and congestion. On the other hand, if you are traveling on another highway that has four lanes, this road allows for more people to travel at the same time, but the speed still remain the same. I hope that makes sense. Okay, so what other benefits can we get from using LACP? So traffic is traveling from one device to another is distributed across multiple links, which allows multiple data streams to be transmitted simultaneously. And that reduces congestion and improves overall network efficiency. If one link fails, traffic can continue to flow over the remaining links, which enhances network reliability and reachability. Okay, what are the use cases? So, you can use LACP when connecting switches, for example, aggregating multiple links between switches. This will help you increase the inter-switch bandwidth and provide redundancy so that you can use both links simultaneously or multiple links simultaneously. So if there are multiple links that interconnect a couple of switches, by default, there will be only one single link that is forwarding traffic because of spanning tree protocol, a topic that we will cover in the upcoming labs. So STP is a loop prevention mechanism that will stop a frame from circulating the network infinitely. So using LACP that create a single logical interface called EtherChannel, allowing the switch to utilize all links under the EtherChannel. Another use case is when connecting to a server. And finally, another critical component is the link between the core and the backbone of your network. This requires high availability, scalability, and high bandwidth to efficiently handle data traffic within and between different network segments. Let's move into the lab objective. The objective of this lab is to provide hands-on experience in configuring and verifying Layer 2 Ether channel using Link Aggregation Control Protocol on Cisco switches. By the end of this lab, you will be able to understand the concept and benefits of EtherChannel and LACP protocol. You will be able to configure Layer 2 EtherChannel using LACP in both active and passive mode. You will be able to verify the operational status and configuration of the EtherChannel, and you will be able to troubleshoot common issues related to EtherChannel and LACP protocol. You will be able to troubleshoot common issues related to EtherChannel and LACP protocol. We will also perform a failover test to make sure that we will have network operation continuity. With regards to the lab topology, we have a couple of departments. These are the IT department that resides in VLAN 10 and the HR department that resides in VLAN 20. PC1 and PC2 are connected to switch 1, and PC3 and PC4 are connected to switch 2. PC1 and PC3 are part of the IT department, and PC2 and PC4 are part of the HR department. Switch 1 and Switch 2 are interconnected via Gig Ethernet 1/1/1, as well as /2, as well as /3. These links will be configured in trunk mode, where the links that are connected to the end hosts will be configured in access mode with the appropriate VLAN in question. So regarding the lab tables, the first table that we are going to tackle is the switch VLAN table. And as you can see on the screen, the table presents details regarding devices, interface configurations, and associated VLANs. You can see the device name column lists the name of the network device. The interface ID column displays the unique identifier of the interface on the respective device. And we can see the interface mode column, and here it indicates the operational mode of each interface, and it specifies whether the interface is configured as trunk or access mode. If it's in trunk, then that means we will allow at least multiple VLANs to go through the trunk. These VLANs are specified in the VLANs column. So for instance, the first one or the first record, say switch 1 as the device name, the interface ID is gig ethernet 1/1/1. The operation mode is going to operate in trunk, and the allowed VLANs or the VLANs that should be allowed through the trunk are 10 and 20. Similarly, with the access mode, this means that the port is going to use a single VLAN for data traffic, and this VLAN can be found under the VLAN column. For example, switch 1, gig ethernet 1/0/1 is going to operate in access mode and is going to be assigned with VLAN 10. Now let's move into the SVI table. Again, device name and interface ID is similar to what we discussed above. The IP address column that shows what each interface will utilize which IPv4 address. And finally, the subnet mask, and that dictate how big is the network address. For example, we can see SVI 10 will be part of this network, which is 192.168.10.10, and the subnet mask is 255.255.255.0, which is /24. And then finally is the end host IPv4 address table. And this is just for your information. In this lab, we configured each end host prior to the lab with the information you see on this table. So for example, PC1 is already configured with 192.168.10.100 with the subnet mask /24 or 255.255.255.0 and is part of VLAN 10. And also we set the default gateway to 192.168.10.10. So with regards to the lab tasks, as you can see on the screen, we have multiple tasks that we have to go through. Some of the tasks we have already tackled in our previous labs. So the first task, for example, we are going to configure VLAN and SVI configuration across both switches, switch 1 and switch 2. And then we're going to move to step 2, where we're going to perform some trunk configuration, again, across both switches to enable the gig Ethernet 1/1/1 all the way to 3 to operate in trunk mode and allow the certain VLANs. And then we're going to move into step 3, where we are going to configure the access ports from switch 1 and switch 2 that are connected to the end hosts. And then step number 4, we already have done that prior to the lab. So we don't need to worry about it unless, obviously, if you are going to create the lab by yourself, either virtually or physically. And then in that case, you would need to go through that step. And then after this, we are going to review the initial configuration. Then we're going to move to step 6, where we are going to create and configure a layer 2 ether channel by using LACP protocol. And we are going to do that across all the links between switch 1 and switch 2. And you can see that this task has subtasks. We're going to go through all of these tasks in the lab. And then we're going to move into step 7, where we're going to check connectivity between PC1 and PC2, and then PC3 and PC2, and PC1 and PC3, and PC1 and PC4. And then once we have done that, we're going to move into step 8, where we are going to mimic a link failure to check continuous connectivity. And what we're going to do, we're going to initiate a continuous ping from PC1 to PC3. And then we're going to observe the output when we shut down one of the interfaces from the lag or from the ether channel and see if we're going to lose connectivity or not. And if we do, how long is that going to take, etc., etc. And then we're going to roll back the changes, and then we move into step 9. And step 9, we're going to reveal or display the current ether channel load balancing mechanism. We're going to find out what method does it uses by default, and then we're going to change that method from whatever the default value is to the source and destination MAC address. And then after that, we're going to perform some in-flight checks. And then finally, if pings were successful and we have reachability and we have no issues, then we are going to save the configuration, and that will be the end of the lab. Okay, so this is the moment where I ask you to pause the video and give this a go yourself to test your knowledge and skills. So I added the lab document in the video description so that you can download it and practice at your own pace. I have also included a couple of packet tracer labs for you to download. You will find a pre and a post version of the lab. The pre-lab is for those who want the lab ready to go and tackle all tasks, and the post-lab is for those who want the full lab solution. So enough of that, and let's dive into the lab solution. So I'm going to tackle the first task, and I'm going to jump into switch 1. And I will start to create the VLANs and also the SVI, as we discussed earlier. And now let's perform some in-flight checks. So I'm going to say show VLAN brief. You can see that we have created these two VLANs. However, we haven't assigned any interfaces yet. which is fine. If I say show IP interface brief, pipe include LAN, you can see that I've created these two VLANs or SVIs, 10 and 20. Let's do the same thing on switch 2. Now let's perform some in-flight checks. These two departments have been created, or VLANs have been created. And also these two SVIs have been created. Next, let's tackle step 2, where we're going to do some trunk configuration. So I'll go back to switch 1. So in this command, I'm using the range command to configure multiple interfaces simultaneously. So I'm going to do that. So I will say description, and I'm going to say link to switch 2, since we are on switch 1. And then I'm going to configure all these interfaces with the mode trunk as per lab requirement. Now let's do the same thing on switch 2. So I would say interface range gig ethernet 1/1/1-3, and we're going to set the description first. And then we're going to say switch port mode trunk. Let's just do some in-flight checks quickly. So we're going to say show interface trunk. You can see that we have configured trunk or static trunk across these three interfaces, gig ethernet 1/1/1/2 and /3. The current mode is on, which means is statically configured. The current encapsulation method is using .1q, and the current status is trunking, and the native VLAN is 1. And here are the allowed VLANs and active at the same time. If I repeat that, if I reissue the command again, you can see here that these three interfaces, suggesting that the interface that is actually in the forwarding state is only gig ethernet 1/1/1, and gig ethernet 1/1/2 and 3 are none because they are being blocked by spanning tree. So if I say show spanning tree VLAN, let's say 10 for example, you can see that gig ethernet 1/1/1 in the forwarding state. However, /3 and /2 are in the blocking state, as you can see on the screen. And also, to prove my point, if I go back to my topology, you'll be able to see that all links are green. The only two links that are not green is the switch to gig ethernet 1/1/2 and /3 from a switch to perspective, as you can see on the screen. Let's do some in-flight checks on switch 1. So we're going to say show interfaces trunk. And here you can see all interfaces are actually active or forwarding traffic, because probably switch 1 is the root bridge. But we are going to talk about spanning tree at some point in the future. So anyway, we get the same output as what we saw from switch 2. Let's move into step 3, where we're going to do some access port configuration. So we would need to configure the ports that are pointing to the end hosts. So I'm going to start with switch 1, and I'm going to go back to global config. And then from here, I will configure interface gig ethernet 1/0/1. I will hit the description command first to say that this is going to be link to PC1. And I'm going to say switch port mode access, switch port access VLAN 10. I will up arrow multiple times to get the same command and change the interface ID from 1 to 2. I'll do the same thing for the description command, and I'll change the description from link to PC1 to PC2. I'll do the same thing with the switch port mode access, and then finally we're going to set the VLAN to 20. Now let's just do some in-flight checks. So we're going to say show VLAN brief. You can see that these two ports are part of the respective VLAN. Let's do the same thing on switch 2. Now let's perform some in-flight checks. Again, we get similar output to what we saw on switch 1. Next, let's tackle step 4. As I mentioned earlier, that this step has already been done. But what I'm going to do, I'm going to go back to the lab and go to a couple of PCs and check their current IPv4 addresses. So let's do that. So that's PC1. If you go to desktop and then IP configuration, you can see that this has been already configured with this IPv4 address, this subnet mask, and this default gateway. Let's do the same thing for PC4. And you can see that we have similar result. So next, let's move into step 5, where we're gonna examine the initial configuration. So I'm gonna go back to switch 1. And I would say show spanning tree VLAN 10. And right now you can see that all ports in the forwarding state. There are no ports that are blocked for VLAN 10. Let's do the same thing for VLAN 20. And the same applies for VLAN 20. And just to let you know, the reason being all ports are in the forwarding state is because this switch is actually the root bridge. Let's do the same thing for switch 2. So if I say show VLAN, show spanning tree VLAN 10. So as we mentioned earlier, these two interfaces have been blocked due to spanning tree protocol, a loop prevention mechanism. And if I do the same thing for VLAN 20, we're going to get the same result. I would like to draw your attention to this because when we configure EtherChannel, this will change. So now let's move into step number 6, where we are going to configure layer 2 EtherChannel by using LACP on ports gig Ethernet 1/1/1 all the way to /3. So we're going to tackle the first subtask, and the first subtask is asking us to use the active mode across gig Ethernet 1/1/1 and gig Ethernet 1/1/2. So we're going to do that now. So I'm going to go back to global config and I'm going to say interface range gig Ethernet 1/1/1-2. And here we're going to say channel group. We're going to say 10. If we question mark that, you would need to specify the group number. This is the content sensitive help that would direct you and will help you understand your iOS syntax. So in that case, I'm only allowed to use any number from 1 all the way to 48. That will vary depending on the software that you're using. So in my case, I'm going to use 10. And then if I question mark that, we would need to specify the mode after that. So I'm going to say mode, and then we would have 2 options or multiple options. And right now we are using the LACP protocol. We are not using the PEGP protocol. So in order for us to use the LACP protocol, we can either use active or passive. With that being said, I'm gonna follow what the playbook is asking me to do. So I'm gonna use the active option and I'm gonna hit enter. Let's do the same thing on switch 1. So I'll go back to global config, and here I'm going to say interface range gig ethernet 1/1/1-2, and I'm going to say channel group 10 mode active. Now let's move into the second subtask where we're going to configure gig ethernet 1/1/3, but we are using the passive mode. So let's do that. So I'm going to say interface gig ethernet 1/1/3, and from here I'm going to say channel dash group, I'm going to say 10, and then we're going to say mode passive. Let's do the same thing on switch 2. Okay, so with that being done, let's move into subtask C. And subtask C is asking us to issue the appropriate command to verify our configuration. So what I will do, I'll go back to user privilege mode, and from here I would say show EtherChannel. So this output indicates the group ID, which is we created EtherChannel 10. And the group state here, it indicates that we are using layer 2. And the protocol here is saying that the current protocol that we are using is the LACP protocol. And the current ports that are configured are 3. We also can do something else. So we can issue this command, show running, and then we're going to say section 1/1/1, and we're going to add the $sign. And you can see this is the current configuration for interface gig ethernet 1/1/1. If we do the same thing for /3, you will see that the channel group is being configured with passive rather than active. Okay, so next let's move into the second subtask, which is D. And D is asking us to issue the appropriate command to check the EtherChannel summary information. And to do this, we would need to use this command, which is show EtherChannel summary. And here we're going to get a summary output of the current ether channels that are being used for this switch. So right now we can see some flags or acronyms. So for example, D or capital D, it means that the interface is down. Capital P, it means that the port is actually in port channel. I, standalone. S is suspended. H is hot standby, etc., etc. You can read that yourself. So let's translate that with this output here. So group, this is the group ID. So we created EtherChannel 10. So this is it. And here it tells you that port channel is 10 is SU. So S, if we look at the S here, it says here is operating in layer 2. And U, it says here that is in use. The current protocol is using LACP, and these are the ports that are part of that Ether channel. So what I want to draw your attention to is that gig Ethernet 1/1/1 and gig Ethernet 1/1/2, both of them are actually in port channel. However, this interface is actually standalone. And the reason why it's not standalone is because it's been configured with passive mode, as you can see on the screen here. Now let's move into subtask E, and this task is asking us to go back to switch 1 and configure gig ethernet 1/1/3 to use active mode. So one side will be active and the other side will be passive. Let's see what's going to happen. So I'm going to go back to switch 1. And here, since I'm already in the interface config mode, let's just verify that I'm on the right configuration or level configuration. And here I'm going to say channel group mode active. That will bring the interface down, but then it will flag it back up again. And from switch 1 perspective, if we say show running and then section or pipe section, and then let's specify the interface ID, you can see that now this has changed from passive to active. Okay, next, let's move into the next step, which is issuing the appropriate command to display the information about port channel 10. So we will need to issue the same command. So I'm going to say show EtherChannel summary. And here you can see that all ports have been part of the Ether channel, as you can see on the screen. Let's do the same thing quickly on switch 2. So previously that was just a standalone and now is participating as part of the Ether channel. Okay, so what I want to show you next is what happens to the current bandwidth for port channel 10. So if you want to look at this information, what you can do, you can issue show interfaces port channel 10. So as you can see on the screen here, this is the current bandwidth in kilobits per second. And here is the also the bandwidth, but in megabits per second. As you can see here, this is 3000 megabits per second. And this is the current bandwidth for this logical interface. Okay, let's move on to the next subtask. And the next one is we are going to execute the command related to spanning tree to display the spanning tree information regarding to VLAN 10, VLAN 20 on switch 1 as well as switch 2. And let's see the difference and do some comparison. So on switch 2, if you remember previously when we issued the show spanning tree VLAN 10, for example, we might need to do some troubleshooting, guys. So I'm going to go back to the Ether channel. So I'm going to say interface port channel 10. I'm going to shut down the interface and I'm going to enable it again. And let's say show Ether channel summary, show IP interface brief. You can see these all three interfaces are in the up state. And the port channel is also in the up state. Let's say show spanning tree VLAN 10. And now you can see that it's been listed in the spanning tree table. I don't know why it didn't work previously, but now it is working. So for some reason you had to flip the interface and that might actually resolve the problem. So what you see on the screen here with regards to spanning tree protocol is that now we see all interfaces are actually in the forwarding state and there are no interfaces that have been blocked. So if I go back to switch 2 or switch 1, and if I say show spanning tree VLAN 10, for instance, you can see that all ports are in the forwarding state. And as I mentioned before, because those three interfaces or three links that interconnect switch 1 and switch 2 are now logically connected as a single logical interface. So spanning tree will treat it as a single interface, and this is where we're going to be able to utilize all links simultaneously. If I go back to the topology, you can see that all links are green, as you can see on the screen. So next, let's move into step 7, where we're gonna initiate some connectivity. We're gonna ping from PC1 to PC3. So let's start with this. So I will go to PC1 and I'll go to the CLI. And from here, I would just need to get the IPv4 address for the other PCs as well, so I can see them. Okay, so from PC1, let's ping PC3. So we're going to say ping 192.168.10.101. And you can see that we have reachability. Let's do the same thing for PC2. So we're going to say 192.168.20.100. That is the IP address for PC2. And it looks like we have a problem. So it's time to do another troubleshooting. So let's go back to our switches. So switch 1, show IP interface brief. So we have seen the SVI, that is the correct SVI for each VLAN. Let's check the VLAN table. So port gig Ethernet 1/0/1, it resides in the right VLAN, and the same applies for VLAN 20. Okay, let's examine the configuration on switch 2. Let's say show IP interface brief. And here we see that VLAN 10 and VLAN 20 with the correct IPv4 address. Let's say show VLAN brief. And that looks good to me. Next, let's just verify the IP configuration on VLAN 20, on PC2. So let's initiate a ping to the default gateway. So that's 192.168.20.10. And I'm able to reach the default gateway, which is good. Let's try to reach switch 2. And I'm able to reach switch 2. Yes. Okay. So I just remembered one of the things that we would need to do is we would need to enable IP routing, and I actually forgot to do that. So let's do that quickly. So we're going to say IP routing. And let's do the same thing for switch 2 as well. And then if I go back to the PC1 and reinitiate the ping again, and you can see that the ping is successful. Okay, so we have reachability to PC2. Let's now test PC4 to PC2. So I'm going to go back to PC4, go to the CLI, and from here, we're going to say ping 192.168.20.100. And we do have reachability. And what about PC3? So PC3 will be 10.100, or would it be 101? And we have reachability as well. Okay, so now what we're going to do, we're going to move into step 8, where we are going to mimic a link failure to check connectivity between each department. So what I'm going to do, I'm going to go back on PC1, and I will initiate a continuous ping. So I'm going to say ping space dash n, and I'm going to say, let's say just like 1000 or 10,000. Let's keep it 1000. And we're going to say the IP address that we want to ping, 192.168.10.101. And before we do that, let's just get switch. Is it switch 1 that we want to shut down the interface from? Yes, so we will do this. So I'm going to go to global config mode, and I'm going to say interface gig ethernet 1/1/1, and I'm going to start the ping from PC1 to PC3. And while the ping is working in the background, I'm going to go back quickly to switch 1, interface gig ethernet 1/1/1, and I'm going to shut the interface. And as you can see from the left hand side, the connectivity hasn't been impacted whatsoever. So I'm going to cancel this. And now that we proved that we haven't lost any connectivity, I'm going to go back and shut the interface. And let's just perform some in-flight checks. You can see that this is up, and all 3 interfaces are in the up state. Next, let's move into EtherChannel load balancing. So the first task or subtask under the task number 9, we will need to reveal the information or the default settings for the EtherChannel load balancing. And to do that is literally easy and simple. What we need to do is we would say show EtherChannel load balance. And as you can see on the screen, the current method that is using is the source MAC address. This means every time the switch receives a MAC address from the source address, it uses one link. And then the second time that a different MAC address comes in to go across the channel or the ether channel, it would have to use a different link, so on and so forth. So let's move into the second subtask, which is subtask B. And in here is asking us to change the load balance method from the default settings, which is the source MAC address, to the source and destination MAC address. And if you want to do that, it's fairly straightforward. You would need to go back to global configuration, and then from here you would need to say port channel load balance, and then if you question mark that to reveal the content sensitive help, you will be able to see all the different methods that you can apply on the switch. So right now what we need, or what we after, is this option here, source dash destination dash MAC. And let's just perform some in-flight checks. So we're going to say show ether channel load dash balance. And you can see that the current settings have changed from source MAC address to source and destination MAC address. So with that being said, we can go ahead and then save the lab, and that will be the end of the lab. So that's it, folks, for this video. If you found this video helpful, please don't forget to give it a thumbs up. And if you haven't already, please hit that subscribe button and turn notifications so you never miss our future tutorials and tech insights. If you have any questions, comments, feel free to drop a comment below. I read all your comments and I'm here to assist you. Remember, consistency and hands-on practice are key to success. So stay curious, stay inspired, and until next time, peace.